Okay. Now, let us say solution of liquid in liquid. Solution of liquid in liquid. Say, first let us know meaning of one important term, that is vapor pressure of liquid. Let us see the definition of vapor pressure of liquid. See, on rising the temperature, liquids begin to vaporize. Why liquids vaporize on rising the temperature is the question. See, all liquids have a tendency to enter into the vapor state, because in vapor state the particles are little bit more free than what they are in liquid state. That's why all liquids have a tendency to enter into the vapor state. The tendency of a liquid enter into the vapor state, or the escaping tendency of liquid into vapor state, is known as vaporization. It's known as vaporization. You just consider a liquid. Okay. Here, on rising the temperature or even at the normal condition, liquid vaporize to some extent, of course to a small extent. At the surface of the liquid, there will be some vapors of that liquid. At the surface, vapors of liquid. Below it, liquid. That means at the surface of a liquid, there you can see two phases. One is the liquid phase, another one is its vapor phase. So at the surface there exists an equilibrium state between the vapors of a liquid, vapors and liquid form. So at this stage, the pressure exerted by the vapors of the liquid, of course at the given temperature, is known as vapor pressure of liquid. Vapor pressure of liquid is the pressure exerted by vapors of a liquid at the surface of liquid, where there exists an equilibrium state between liquid and its vapors at the given temperature. That is definition of vapor pressure of liquid. See, the vapor pressure of liquids varies from liquid to liquid, and it depends upon nature of liquid as well as temperature. Temperature and nature of liquid plays significant role on their vapor pressures. See, more volatile liquids, volatile liquids. Volatile liquids are those liquids which can vaporize even at ordinary temperature. Example, benzene, toluene, carbon tetrachloride, chloroform, etc., etc. See, the vapor pressure or the more volatile liquids which have very low boiling points show high vapor pressures. More volatile liquids show high vapor pressure, whereas high boiling point liquids, say non-volatile liquids, show low vapor pressure. Generally, volatile liquids or liquids which have low boiling points show higher vapor pressure, because they can easily enter into the vapor phase. They can easily vaporize. As a result, amount of vapors increases. Consequently, pressure also increases. Okay. So, on rising the temperature of any liquid, you take it from me, on rising the temperature of any liquid, vapor pressure of that liquid increases because of increase of vaporization or amount of vapors at the surface of the liquid. Now, let us consider solutions of liquid in liquid. Solutions of liquid in liquid are the homogeneous mixtures of two or more than two liquids, of which one liquid acts as solvent, the rest act as solute. Okay? Of course, the state of such solution will be liquid, because solvent is in the liquid state. Now, if a liquid in liquid solution made of only two liquids, solution is made up of only two liquids, one is solute, another one is solvent. Okay, the action or selection depends upon the nature of the liquids considered. So, a solution is made up of only two liquids, then that solution is known as binary solution or binary liquid mixtures. A binary liquid mixture is one which consisting of only two liquids, of which one is solute, another one is solvent. Example, benzene toluene mixture, ethyl alcohol water mixture, hydrochloric acid water mixture. They are all few examples for binary liquid mixtures. See, after studying the vapor pressure of number of binary liquid systems, binary liquid mixtures, Raoult had framed a relationship or developed a relationship. Raoult framed a relationship between the partial pressure of vapors of the liquid, constituent liquid of solution, and its mole fraction in the solution. That relationship is known as Raoult's law. Raoult's law gives a relationship between the vapor pressure of more volatile constituent of a liquid mixture and its mole fraction in the solution. And Raoult's law states the vapor pressure or partial pressure of more volatile constituent of a binary liquid mixture is directly proportional to its mole fraction in the solution. That is, P is directly proportional to chi. P stands for partial pressure or vapor pressure of the constituent. Chi, its mole fraction in the solution, or P is equal to P naught into chi. This is Raoult's relationship or Raoult's law expression. You just consider a solution is made up of two liquids, A and B. A solution is made up of two liquids, A and B. For liquid A, we can write Raoult's expression as Pa is equal to P naught A chi A. Here P naught, it is actually a constant term. It is known as pressure of the liquid in its pure state. Pressure of that liquid in its pure. See here, this is pressure of the constituent liquid in its pure state. P, partial pressure of that liquid in the solution. It is pressure of one of the constituent in the solution. It is pressure of that vapor pressure of that liquid in its pure state. So, Pa is equal to P naught A chi A. Similarly, for the constituent B or component B, it is Pb is equal to P naught B chi B. Here P naught A and P naught B are the vapor pressures of liquids A and B in their pure state. Okay. Pa and Pb are the partial vapor pressures or partial pressures of liquid A and liquid B in the solution. Chi A and chi B are the mole fractions of liquid A and liquid B in solution. Okay. Now, to just see this expression, P is equal to P naught chi. Here chi is a variable term. That means composition can be varied. Composition of the solution can be varied. So, chi is a variable term. P naught, that is vapor pressure of pure component, is always constant. It is fixed. P, it is partial pressure or vapor pressure of constituent in the solution. It also varies. When you change the value of chi, that is mole fraction, concentration of the solution, then the component partial pressure also changes. So, P is a variable term, chi is variable term. You just consider this mole fraction term as x, this constant term P naught as m, and P as y. We can take this one as plus 0 also. Now, this is an equation for straight line. This indicates the Raoult's law expression is also in the form of straight line equation. Raoult's law is in the form of straight line equation. So, the plot of mole fraction of a constituent of liquid mixture, mole fraction of constituent of liquid mixture against its partial pressure must be a straight line, because this expression is in the form of straight line equation. Okay. So, plot of partial pressure of a constituent against its mole fraction in the solution at the given temperature is constant. Sorry, is a straight line and pass through the origin. The straight line passing through the origin. That is, of course, the slope of the straight line must be equal to P naught of the solution, liquid. That is vapor pressure of that liquid in its pure state. It is one important aspect. Now, let us see this system, that is system or solution containing the constituent liquids A and B. For the liquid A, Raoult's equation is Pa is equal to P naught A chi A, and for liquid B it is Pb is equal to P naught B chi B. You know Dalton's law of partial pressure. Dalton's law of partial pressure states the total pressure of a mixture is equal to, of course, mixture of gases, mixture is equal to sum of the partial pressures of individual or constituents. That is, P total, it is nothing but capital P stands for total pressure. Total pressure is equal to sum of the partial pressures of the constituents, that is Pa plus Pb. We know that Pa is equal to P naught A chi A and Pb is equal to P naught B chi B. Okay. Now, you know another relationship. For a system, the sum of mole fractions of all the constituents is simply equal to unit 1. Sum of the mole fractions of all the constituents is simply equal to 1. That is chi A plus chi B, which is equal to 1. Or you can say chi A is equal to 1 minus chi B, or chi B is equal to 1 minus chi A. Okay. Chi A is equal to 1 minus chi B. Chi B is equal to 1 minus chi A. Now, you just put the value of either chi A or chi B in this expression. Okay. That is, P is equal to, what is capital P? Total pressure of the system. It is nothing but sum of the partial pressures of individual liquids or constituent liquids. P is equal to P naught A into chi A is 1 minus chi B plus P naught B chi B. Okay. You can expand this one. P naught A minus P naught A into chi B plus P naught B chi B. Okay. Or you can write P is equal to P naught A plus P naught B minus P naught A into chi B. Okay. This is another form of Raoult's law or Raoult's equation. Here, P naught A and P naught B, you know that partial pressures of pure components are constants. Partial pressures of pure components are constants. Excuse me. Okay. Partial pressures of pure components are constants. Chi B, what is chi B? It is mole fraction of one of the constituent of the solution. Similarly, you can write P is equal to P naught B plus P naught A minus P naught B chi A. You can also write that one. That is, you will get that expression when you substitute with the value of chi B in this expression. Okay. Now, we can say it is constant term. Let it be C plus these two are constants. P naught B and P naught A are constants. Difference between two constants must be a constant. Let us consider this constant as M. It is a variable term. Let it be X. P, total pressure also variable one, because on changing the composition, pressure of the system also varies. So, P is variable Y. Once again, shows this form of Raoult's equation is also in the form of straight line equation. Okay, this is one important thing. Now, let me plot graph taking total pressure against the mole fraction of constituent, or pressure against partial pressure of each component against their composition or mole fraction. You will get a plot something like this. Okay, this is partial pressure. Now consider here mole fraction of constituent A is 1. That means at this point pure A is present. Only the component A present, where the component B is not present. Only pure A is considered, where when you consider pure liquid, its mole fraction will be 1. That is, chi A is equal to 1, chi B is equal to 0. Chi B is 0 means at this point there is no component B or liquid B in the mixture. In the system, only liquid A present. Okay. Similarly, consider this point. Here, liquid A is 0, where its mole fraction is 0. And here, pure liquid B present, where its mole fraction is 1. In between these 2 points, both A and B are present in different amounts, different proportions. Okay? That means the constituents have different mole fraction. That means here mole fraction of A at this point, you can say mole fraction of A is 0.9, mole fraction of B is 0.1. You know that sum of the mole fractions of all the constituents of a system is simply equal to 1. Here, if mole fraction of A is 0.8, then mole fraction of B will be 0.2. That means on moving from left to right side, mole fraction of A gradually decreased, where mole fraction of B is gradually increased. That means on moving from left to right in the plot, concentration of B in solution or amount of B in solution increases, amount of A decreases. That is, say as per your Raoult's equation, that is P is equal to P naught chi, let's say for liquid A, P naught A chi A. Similarly for liquid B, it is P naught B chi B. Okay. If you plot a graph taking these two expressions or considering these two expressions, for liquid A, you will have a plot like this. That is, you know, plot of P against chi is a straight line. Plot of P against chi is a straight line passing through the origin. For liquid A, you will have a plot like this. Okay. And for liquid B, you will have a plot like this. Okay. This pressure, that is where pure liquid A present, you can call it as P naught A. Whereas here pure B present, you can consider this one as P naught B. You will have a plot like this. That is for pure components, that is liquid A and liquid B. This plot corresponds to this equation, that is Pa is equal to P naught A chi A. This plot corresponds to Pb is equal to P naught B chi B. Okay. Now you consider the mixture. Okay. And observe the vapor pressure of mixture, that is total pressure of the mixture at different composition, different mole fraction. That is, by making use of this equation or this expression, plot the graph, which you will get something like this. So this plot for the mixture, these two for the constituent liquids, and this can be written as, or P is equal to P naught A chi A plus P naught B chi B. That is. Okay. See, here this plot indicates for a given binary liquid mixture, the combined vapor pressure, that is vapor pressure of the mixture, a different composition lies in between the vapor pressure of pure components. P naught A, P naught B are the vapor pressures of pure components. So, the combined vapor pressure lies in between the pure components vapor pressure, and plot is linear. Okay. This is one important thing. So, mixture, in case of binary liquid mixtures, the total pressure or combined vapor pressure of the mixture lies in between the vapor pressures of two pure components at any composition, any temperature. That is importance of Raoult's law. Now, it is considered the liquid mixtures which show the combined vapor pressure is in between the vapor pressures of pure components are known as ideal liquid mixtures. So, it is found that some binary liquid mixtures strictly show or obey the Raoult's law. They show the vapor pressure of mixture at any composition, the given temperature, is in between the vapor pressures of two liquids. Such liquid mixtures are considered as ideal liquid mixtures. But some liquid mixtures show the combined vapor pressure will be either higher or lower than the vapor pressures of pure components. Such liquid mixtures are known as non-ideal solutions. So, binary liquid mixtures are of two types. Some binary liquid mixtures follow the Raoult's law, in which vapor pressure of mixture at any composition temperature is in between the vapor pressures of two constituents or components, pure components. In some cases, it will be either higher or lower than the vapor pressures of pure constituents. So, there are two types of binary liquid mixtures, one which obeys Raoult's law strictly at all temperature and composition are known as ideal solutions, and those which do not obey the law are known as non-ideal solutions. So, binary liquid mixtures or solutions are of two types: ideal solutions, non-ideal solutions. I will give some examples for ideal and non-ideal solutions. Ideal solution, benzene toluene mixture, mixture of benzene toluene, carbon tetrachloride, silicon tetrachloride. Non-ideal solution, mixture of ethyl alcohol and water, mixture of hydrochloric acid and water, mixture of ethyl alcohol and water, so on and so forth. There are few examples for non-ideal solutions. Now, let us see the characteristics or differences between ideal and non-ideal solutions. Ideal and non-ideal solutions. Okay. Ideal solutions, non-ideal solutions. First, the definition can be taken as the difference or characteristic. So what is an ideal solution? An ideal solution is one which strictly follow the Raoult's law at all composition, or that means concentration and temperature. That means obey the Raoult's law. Automatically, non-ideal solutions do not obey the Raoult's law. They deviate from the Raoult's law. Okay. So, not obeying the Raoult's law. The solutions, non-ideal solutions do not obey the Raoult's law, do not follow the Raoult's law. Whereas ideal solutions follow the Raoult's law. 1 point. Next, see, you can give what you have observed. In case of ideal solution, the combined vapor pressure means vapor pressure of mixture, that is solution. The combined vapor pressure of system lies in between the vapor pressures of pure components. Okay, regarding vapor pressure difference, let us see. Here the vapor pressure of mixture lies in between the pure components vapor pressure at all composition. Here the vapor pressure of the mixture lies above the vapor pressure of pure components or below the vapor pressure of pure components. So here above or below the vapor pressure of pure components. Next one is, here you just see, in case of ideal solution, enthalpy of solution is 0. Enthalpy of solution 0 means heat neither liberated nor absorbed. That is, mixing process, formation of solution process is neither exothermic nor endothermic. Heat not liberated, heat not absorbed. So delta H of solution 0. Enthalpy of solution is 0. Here, in the case of non-ideal solution, okay, enthalpy of solution is either positive or negative, but not 0. That means it is thermoneutral, but it is either exothermic or endothermic. During the preparation of the non-ideal solution, heat may be liberated or heat may be absorbed. That is, process may be exothermic or endothermic. Next difference is volume change of solution is 0. Volume change of solution is 0. That means there will be no change in volume in case of ideal solution. In case of ideal solution, volume of solution will be equal to sum of the volumes of constituent liquids. Case of ideal solution, sum of the volumes of constituent liquids will be the volume of the resultant solution. That means if you mix 5 ml of benzene and 5 ml of toluene, here site stands for C6H5 group, 5 ml of toluene and 5 ml of benzene, the resultant mixture will be 10 ml. The resultant mixture will be 10 ml. What do you mean by delta V? Delta V is nothing but final volume minus initial volume. Here final volume is 10 ml. Initial volumes will be 5 plus 5, 10. So 10 minus 10, 0. That means there is no change in volume. It is not so in the case of non-ideal solution. In the case of non-ideal solution, delta V will be either positive or negative. That means during the formation of non-ideal solution, volume decreases or increases. After mixing, the volume increased or decreased. That means in the case of non-ideal solution, the volume of solution will not be equal to the sum of the volumes of constituent liquids. It will be either greater than that or less than that. Okay, it is for different reason. Later we shall see that. Next one is, in the case of ideal solution, the properties are additive. The properties of ideal solution are additive. That means, in the case of mixture of benzene and toluene, you can see the properties of benzene as well as the properties of toluene. So, properties are additive. Here, properties are not additive. They give different properties altogether. Okay. Next, here, that is properties. Next difference is the activity of solution is proportional to mole fraction. In case of ideal solution, the activity of solution is directly proportional to mole fraction of solution or constituent. Here it is not so. Activity is not proportional to mole fraction. Next one, difference is, here in the case of ideal solutions, the intermolecular interaction between the two liquids in the solution, the intermolecular interaction between the two liquid particles will be same as that exists in the pure liquid. That is, interaction between AB, where A is particle of solution in solvent A, B is particle of solvent B. This is in the solution there will be interaction between these two particles of two different solvents, liquids. This intermolecular interaction is same as that exists in the pure state of the liquid, that is AA and BB. It is not so here. The intermolecular force of interaction or intermolecular interaction is not equal to that exists in the case of pure liquids. Lastly, but not least one, in case of ideal solutions, we can separate the constituents into their pure form by fractional distillation method. Here, from the mixture of benzene, of course, mixture of benzene and toluene is an example for ideal solution. From the mixture, you can separate benzene into its pure form, toluene in its pure form by fractional distillation method. It is not so here. That means, ethyl alcohol and water is an example for non-ideal solution. From the mixture of ethyl alcohol in water, you can't separate pure ethyl alcohol by fractional distillation. Okay? You can't separate ethyl alcohol as well as water from the mixture in their pure forms. That is by fractional distillation method. These are few characteristics or differences between ideal and non-ideal solutions. I'd like to stop here. Next we'll continue.